Have you ever noticed that sounds change their pitch when they're traveling past you? Let's say you're sitting at a stoplight, minding your own business, when all of a sudden you hear an ambulance. The siren wails a high pitch from half a mile down the road. You see the approaching vehicle and wait patiently while the ambulance speeds through the intersection. Once it passes, you notice the siren sounds different. It has a lower pitch than it did before. Why does the sound of the siren change? This common occurrence happens because of something we call the Doppler effect. You may have heard about this before. The Doppler effect explains how we perceive changes in sound when the source of the sound is moving. While the ambulance siren doesn't change pitch at all, we perceive that it changes as the vehicle moves past us. The Doppler effect isn't just about ambulance sirens, though. It's an important phenomenon that occurs in all types of waves: sound waves, light waves, and even water waves. Scientists have used the Doppler effect to make some amazing discoveries. Let's learn a little more about this phenomenon so we can see why it's so important. We already know that a wave is caused by the disturbance of a medium. Let's say you're standing at the edge of a lake when Nessie the Loch Ness Monster pops her head up right in the center. Nessie's head causes a disturbance that travels outward as a circular wave. It takes a bit of time to reach you standing at the bank, but if the lake is perfectly circular, then the wave reaches the opposite edge at exactly the same time. If Nessie keeps bobbing her head up and down, she creates more circular waves moving outward from her head. These waves all reach the bank at a certain frequency, the same frequency as Nessie's head bobbing. If she bobs her head 2 times every second, then that's the frequency of the waves hitting the bank. Now, suppose Nessie begins swimming toward you, still bobbing her head 2 times every second. The circular waves begin to look much different. Because Nessie is traveling some distance between each head bob, each successive wave originates from a slightly different spot on the water. The waves bunch together right in front of Nessie's head and spread out behind it. From your perspective, it looks like Nessie must be bobbing her head faster because the waves coming toward you arrive at a higher frequency. You might even see 3 or 4 waves per second instead of just 2. Even though the actual frequency of the wave source hasn't changed, the apparent frequency is higher. In talking about how an observer perceives waves, we have to be clear about the difference between actual and apparent frequencies. Actual frequency is just what it sounds like. It's the true frequency of a wave, irrespective of external factors. The position of an observer does not affect the actual frequency of a wave. On the other hand, apparent frequency is the frequency perceived by an outside observer. It may or may not match the actual frequency. Before Nessie started swimming across the lake, the apparent frequency you observed was 2 waves per second, the same as the actual frequency. Once Nessie began swimming, the apparent frequency changed. The apparent upward or downward shift in frequency due to the movement of a wave source is called the Doppler effect. According to the Doppler effect, the observer perceives an upward shift in frequency when the wave source is approaching. When you were the observer being approached by Nessie, you perceived an upward shift in the frequency of the waves. Of course, if you were standing on the opposite edge of the lake and Nessie was swimming away from you, you would have observed the waves to be less frequent. The observer perceives a downward shift in frequency when the wave source is retreating. We've seen how the Doppler effect can work in water waves. What about sound waves? What about that ambulance siren we talked about? An ambulance with a ringing siren makes a sound with a certain frequency, the same frequency all the time, whether the ambulance is moving or not. Let's say the sound's frequency is 440 Hertz, so that's the actual frequency. Now pretend you're sitting at that stoplight, and the ambulance is speeding toward you at 50 miles per hour. The sound waves emitted from the vehicle's siren are bunched up in front of it because of its movement through space. The air compressions are closer together. So when the sound waves hit you, you perceive a frequency that is higher than the actual frequency, maybe around 480 Hertz. This is the apparent frequency. Once the ambulance passes you by, the sound waves keep coming, but now they're more spread out. They arrive at your ears at a frequency lower than that of the actual siren, because the ambulance is moving away from you. Perhaps you hear an apparent frequency of 400 Hertz. Overall, you perceive the ambulance to drop the pitch of its siren by 80 Hertz. It really seems to you that whoever's ringing the siren suddenly changed the sound's pitch. But really, the actual frequency is the same, right in the middle at 440 Hertz. If this ambulance could travel fast enough, it might get the sound waves to compound upon each other right at the front of the vehicle. To do this, the ambulance would have to travel at the speed of sound, which is roughly 330 meters per second. Some airplanes can fly at the speed of sound. When they do so, their sound waves completely bunch together in the front, producing what we call a shock wave. A shock wave is a very abrupt disturbance in a medium. The airplane creates the shock wave by making the sound waves merge together. Since it's traveling at the speed of sound, each individual sound wave has no time to get out of the way before the next wave comes. The waves compound on top of each other to create one giant shock wave. If you could listen to this wave, what you would hear is called a sonic boom. Sonic booms are extremely loud sounds caused by the buildup of sound waves. You're most likely to hear a sonic boom from a supersonic aircraft, that is, an aircraft traveling faster than the speed of sound. If you're standing on the ground when this aircraft passes you by, you'll get hit with the edge of a wavefront that is shaped like a cone. This cone shape is caused by the successive spheres of sound waves coming from the airplane. At the edge of the cone, all of the compressions merge together to make one giant sound. When that high-pressure zone hits you, you experience it as a sonic boom. Can the Doppler effect work for light waves too? Of course. Light waves have frequencies too, don't they? A light wave's apparent frequency can change based on the movement of the light source or the movement of the observer. Remember that the frequencies of visible light range from 430 terahertz, which we see as red, to 790 terahertz, which we see as violet. Let's say I had a light source that was somewhere in the middle, like 600 terahertz. It looks greenish-yellow. And let's say my light source was on top of an alien spacecraft. If you were standing in a field and my spacecraft flew quickly toward you, you may perceive the spacecraft as having a greenish-blue light. That's because the apparent frequency of its light waves would be slightly higher than the actual frequency. This phenomenon is known as a blue shift, an increase in a light wave's apparent frequency due to the wave source approaching the observer. The opposite of a blue shift is a red shift, which is a decrease in the light wave's apparent frequency due to the wave source retreating from the observer. You would see a red shift happen with my alien spacecraft if I had it fly quickly away from you. The light wave spreading out behind the retreating spacecraft would decrease the apparent frequency. You'd probably see it leaving with a yellowish-orange light. We don't often experience red and blue shifts in everyday life, but astronomers observe them all the time in the galaxies surrounding them. Galaxies that are moving toward the Earth have a high apparent frequency, that is, they exhibit a blue shift. Galaxies that are moving away from the Earth exhibit a red shift. In the early 1900s, Edwin Hubble and Vestos Slipher got the idea that they could use the Doppler effect to track the movement of galaxies. They began measuring the red and blue shifts of all the galaxies they could find. When they put all their information together, they saw that most galaxies are moving away from the Earth. They also figured out that each separate galaxy is moving away from every other galaxy. In other words, everything in our universe is moving further and further apart. This discovery led astronomers and physicists to conclude that the universe is expanding, a key element which supports the modern Big Bang theory. Back here on Earth, we can still appreciate the Doppler effect for explaining the phenomena we observe in waves. It tells us why the apparent frequency, which is perceived by an observer, is not always the same as the actual frequency. The Doppler effect is the apparent shift in wave frequency due to the movement of a wave source. The apparent frequency shifts upward when the wave source is approaching, and downward when the wave source is retreating. The Doppler effect explains why we perceive a change in pitch of the sound of a passing siren. It also explains the presence of shock waves and sonic booms when observing supersonic aircraft. Light waves, too, can exhibit the results of the Doppler effect. An apparent blue shift occurs when a light source is approaching, and an apparent red shift occurs when it's retreating. Edwin Hubble and Vestos Slipher used the red and blue shifts of our surrounding galaxies to draw conclusions about our universe. Thanks to their discoveries, we now adhere to the modern view that the universe is continuously expanding.